Bless you. Okay, welcome back. I hope you had a good weekend. We are going to continue what we had started last time, which was a new chapter, right? We're chapter 4. So 4.1 is what we're going to start with, but I wanted to give you kind of a big picture here of what we're trying to do. When it comes to functions, we're either going to be looking at them on a closed interval, which means that the function starts at some point A and then ends at some point B, right? So we're only looking at the function on this little, like this little window, and that's the only place we're worried about the function. And so what we can do is, if we have a function that is continuous, that's part of what we need, on a closed interval, then we can always find the absolute maximum or global maximum and minimum of the function. So on this particular picture, this point right here would be our global min, right? And this point right here would be our global max. And remember, the word global can be switched out for absolute. Okay, so you could have your absolute maximum, absolute minimum. So from here on, okay, as you go into computer science, engineering, whatever it is your major is, if someone ever presents you with a function that is continuous on a closed interval, you can always find the highest and lowest points on that graph by using this closed interval method. All right, and that's what we're going to do today. Then after that, we will do this. We will say, okay, say you have a continuous function, but you are not on a closed interval. So it continues to go maybe one direction forever, or the other direction, or both directions, but it's not on a closed interval. Then you have a completely different method, and it doesn't allow you to find the global max and global min. It allows you to find the local maximums and minimums. So that means we'll be able to find that point, that point, that point, right? Now in this particular case, this is the global max, right? But that's going to be difficult for us to show. It's going to need a little more work to show that that's the global max than over here. It's very easy to figure out what the highest and lowest points are. Here we can find the points, and then we have to somehow figure out if we can determine that that's the highest point. All right, so I understand there's two different pictures up here, two different methods. Okay, so start with the easier one first, this one. And this goes for any function, okay, as long as it's continuous. So if you're looking at a profit function for business, you're looking at the profit function, you want to find the highest and lowest points. If this is anything you can think of in the real world, any function, we'll be able to do this. So this is a big deal, what we're doing here today. All right, so here it is. This is how we do it. So if somebody gives you to find the absolute maximum, well, I said global, absolute, right? So absolute, maximum, and minimum values of a continuous function on a closed interval AB, here's the steps we're going to take. The first step is we will find the critical numbers of the function. So do you remember what the critical numbers were? They're critical, right? But remember? No? I have to go back to the previous. There it is. That's the definition from last class. The critical number of a function is a number where one of two things is happening. Either the derivative is 0 there, or the derivative doesn't exist there. So anywhere when we take the derivative of the function, anywhere we get 0, anything that makes that derivative 0, or anything that makes that derivative undefined or not exist, will be a critical number. All right? So the first step to this closed interval method is to figure out where the derivative is 0 and where it's undefined, or not, where the derivative doesn't exist. That's the first step. Okay? Then what we're going to do is we're going to evaluate the function at the endpoints of the, Step 1, find the critical numbers and then evaluate the function at those critical numbers. So we're going to figure out, where the derivative is 0, where it doesn't exist. We're going to take those x values and plug them into the original function and figure out what it spits out. And then we're going to take the two endpoints, that's step 2. We're going to take the two endpoints of the interval and plug those into the function. And then we're just going to compare the answers. And the biggest number we get out is the max, and the smallest number we get out is the minimum. And the geometric idea here is this. I don't know if I can show you this geometrically, but I'll try. Let's say we have a continuous function on a closed interval like that. Then the highest point and the lowest point is either going to happen at the endpoints, right? It's either going to happen at the endpoints, or it's going to happen here or here, where we have what? Derivative is 0. Derivative is 0, right? Now what about the does not exist? What about that picture, right? Someone came up and drew this last class, right? That's an absolute maximum, isn't it? Yes. Right? But that's occurring where the derivative doesn't exist. So our global max and min is either going to be at the endpoints where the derivative is 0 or where the derivative doesn't exist. Make sense? Yes. Okay. So let's go and do our first example. And we're going to do something that you should actually be able to do right now without calculus. We're going to take the function f of x equals x squared plus 3x plus 2. Okay, that's a parabola back from college algebra. Which way does this parabola open? Up, right? Opens up. So we can find that bottom point by using the vertex formula, right? Okay, but we need to get this thing on a closed interval. Okay, so let's get this thing on a closed interval. Let's look at this on the interval 0, 4. And I want us to find the absolute, I'm just going to put abs, max, and min. Okay, that's an and symbol. Find the absolute maximum minimum of this function. All right, so first things first, we look at it. Is it continuous? Why? Why is that continuous? So, yeah, there's nowhere where it doesn't exist. If you go back to the section we did on continuity, which was a long time ago, we said that all polynomial functions are continuous everywhere. And this is a polynomial function. So you draw without picking up your pencil. So if you go back to that section, there's a whole list of like what qualifies as being continuous. Go back and refer to that, but I'll mention it as we go through examples. So this is a polynomial function. It is continuous. So we have a continuous function on a closed interval. So we're only looking between 0 and 4. We'll graph it in a second. And we want to know where the absolute maximum is, right? Okay, so first step is to find the critical numbers. So what I need to do is I need to take the derivative and set it equal to 0. That's the way I'm going to write it. So that's the first thing I'm going to do. So let's take the derivative. What's the derivative of that function? So 2x plus 3, right? And now I'm going to set that equal to 0. So I take 2x plus 3, set it equal to 0, solve for x, we get negative 3/2. Right? Okay. Now, the next thing I need to do is figure out where's the derivative not exist. And this is more of a question. Like, does the derivative not exist? Well, does it? What is the derivative again? This right here. But that's a polynomial, isn't it? 2x plus 3 is a polynomial. That exists everywhere. This right here itself is continuous. There's no problems with this function. If we plug a number in here, we're never going to get division by 0. We're never going to get square roots of negative numbers. There's no problems. This is a well-behaved function. Therefore, this never happens, right? So, no, okay? No problems there. So we only have one critical number, right? What is the critical number? -3/2, right? -3/2. That's our only critical number. So what we're supposed to do is take this and plug this number into what? The original function. But we have a little bit of a problem. Do y'all see the problem? What? Yeah, so the critical number we got right here is not inside this interval, which means that we are going to throw it out. Okay, you always have to check for that. This critical number is not in 0, 4, so we're not allowed to look at it. We are not allowed to consider that, which means we do not have to plug it into the original function. Make sense?
So it does exist, it's just not...
It does exist, but it's outside the window of where we're looking. Okay? When we graph it, you'll see, I think you'll see it all come together. Which means that when we go to step 2, which is to plug in the endpoints, that means our absolute max and min are going to happen at an endpoint. They have to, because we have no critical numbers between 0 and 4. So I go to step 2 now. Step 2, I need to take the endpoints and plug them into the original function. Okay? Plugging the endpoints 0 and 4 into the original function and just see what it spits out. So if I plug in 0, I get 2. That's the easy one, right? What about if I plug in 4? 16 plus 12 plus 2. All right, what is that? 30? 30. Okay. I think it's clear from that our maximum is 30, right? This is the absolute max. And this is the absolute minimum. So when we're talking about what's the absolute maximum and absolute minimum, we are talking about the y coordinate. Okay, that's what we're talking about. It's the value of the function. So the answers are 2, absolute minimum, and 30 is the absolute max. So let's go ahead and graph it. This is our first example, so we're just getting kind of warmed up here. It was a pretty easy function to differentiate, right? Pretty easy to set it equal to 0. What's going on here? Come on, hurry up. Hurry up. Desmos isn't working. All right, well, we'll graph it here then. X squared plus 3x plus 2 on 0, 4. Let's see if it can interpret that. Whoa. Something is wrong with the web right now. What are we going to do? Performing a handshake. I'm just wondering if it's the network or Desmos itself. It looks like it's network.
Try another website?
Yeah, I tried Wolfram Alpha. It worked. Okay. Try this. Wow. Wolfram was supposed to be smart. I really do think there's a network problem right now. Oh, there we go. Okay, here we go. There it is. Do y'all see it? This is the graph of that parabola from 0 to 4. So you can see that the lowest point happened here at the left end point, and the highest was over here at the right end point, up at 30, right? Yes?
So those are Y values, right?
Yep, they're y values.
But how come you were considering an X value and another one?
Why, how come this is telling us where it's going to happen. Is that what you're,
Oh, okay. So you plug that into that, and then that would give you.
that gives you your y coordinate,
There you
yes.
go.
See, we know that the maximums, or max and min is going to occur either at the endpoints or at the critical numbers. The critical number we got isn't inside of our intervals, so we threw it out. Now, I just graphed it again, but this time I didn't do it on a closed interval. So there's the parabola, right? There we go. Let's see if Desmos is back. Nope. Okay, so here's the graph of the function, and you can see that there is something interesting happening. Where's the lowest point on this graph? Where does it look like? About negative 1.5? Isn't that? Right? So our calculus found where something interesting is happening, but it wasn't where we were looking, so we threw it out. So if I change this problem, we redo the problem, and now I say, I don't know, let's go negative 5 to 2, right? Then the problem is different now, right? Now we're only looking, we're looking from negative 5 all the way to 2 over here, and so now we're going to get possibly different answers.
Just plug, you plug X in. You plug into X.
Plug what in? These or this? All of them. The endpoints and this value all get plugged into the original function for x. Yep. So let's work through this. This is a new example. All I've done is change the interval. All the work's pretty much the same, right? First step is we take the derivative, set it equal to 0, right? So we took our derivative. I'm just writing it so we have it. The derivative of that function is 2x plus 3, right? We solve it and we get this. This time, that is in there, right? This is in here. So this is a good point. This is a good critical number. But it's still, we don't have this still, right? So now when we go over here to step 2, step 1, we have to plug it in, sorry. Let's plug that in, still in step 1. Let's take our critical number and plug it into the function. And that means, yes, you have to plug it in, okay? So that means you have to do negative 3 halves squared plus 3 times negative 3 halves plus 2, right? That's what you have to do. So this is squaring a negative gives you positive, so 9/4. If you do this right here, you can get minus 9 halves and do plus 2. And you'll probably need to get a common denominator now. So 9/4 minus 18/4 plus, let's see, 2 on the top or 4 on the top and bottom, 8/4. So that's me getting common denominator. Put it all together, what do you get? I think I'm getting negative 1/4. Right, this together is negative 9/4. Then I'm adding 8/4. So that should be negative 1/4. Okay? Step 2, I have to plug the endpoints in. So f of negative 5, f of 2. Let's do that. So negative 5 in there, squared plus 3 times negative 5 plus 2. So 25 minus 15 plus 2, which is 15. Is that right? No, wait. What? 12, right? Okay, 12. And then here, 2 squared plus 3 times 2 plus 2, which is what? 4, 6, 10, 12. 12 again? Interesting. Okay, so what is our conclusion? This number right here, right, is going to be our global minimum. or absolute. I'm using both because I want you to understand that you can use both. This is our global minimum. And this occurs when you plug -3 halves in, right? So if you go to the graph, you go -3 halves on the x-axis, you're going to go down 1/4, right? But what about the absolute max? What's the absolute max? It's 12, right? But that absolute maximum happens to occur at 2 places. That's not important. The important part's that it's 12. But it's occurring at both endpoints. And that's just the way I picked it. I didn't mean for that to happen. I just got lucky, I guess. Let's see if Desmos is back. Come on, you can't be. Oh, there it is. X squared plus 3x plus 2. There we go. So there's our graph, right? And let me see if I can remember how to do this. Where's our interval? -5 less than equal to x less than equal to 2, right? Hold on. Who helped me do this last time? Someone helped me in here, right? I think it was a brace. Yeah, we have to put it in braces. Got to zoom out a little bit. There we go. So it graphed it on that interval. So again, I got kind of lucky that the 2 endpoints were the same height and lowest point there. Okay? So do you understand fundamentally like what we need to do? I present you with a function. You take its derivative, set it equal to 0. Take its derivative, figure out where it's undefined. Make sure those points lie within the interval, and then you're just comparing. That's all you're doing. Okay. Now the functions get harder. But that's the fundamental idea. Because what's the point of doing a parabola? Parabolas, we can already find the max and min using vertex formulas, so let's do something worse, okay? Let's do something worse than a parabola. I'm going to try and keep it within what the book is asking you, because I can start going off doing crazy stuff. I don't want to get too crazy here. All right. Okay, let's do this one. We'll stick with a polynomial. But we'll make it a harder polynomial. So let's go with this one. Okay, I changed my mind. I'm making it up. 4x to the 5th minus 3x to the 4th plus 1 on the interval -1 to 4. All right, you ready? Let's appreciate, first of all, that that's a pretty nasty function, right? If you can't graph that easily, like in college algebra, we do have some techniques to try and graph that. You know, leading coefficient test, like we know it goes down on the left and up on the right, and you know, it's got maybe so many turns or something like that, but who cares? Let's figure out on that interval if we can find the highest and lowest points on it. So let's take the first step, which is to take the derivative. We're going to need the derivative. Let's just take derivative to start. How about that? So what is our derivative? 20x to the 4th minus 12x cubed. That's our derivative, right? Now we need to set it equal to 0. So let's do that now. Where's that derivative equal to 0? Well, let's see. Where is 20x to the 4th minus 12x cubed equal to 0? So how do I solve that equation? Factor, right? Pull out a 4x cubed, I believe is our GCF. Greatest common factor, 4x cubed. Pull that out. What are we left with in there? 5x minus 3 equals 0. And now that we factored it, we set each factor equal to 0. So if you set this equal to 0, what do you get? What's 4x cubed equals 0? What's the only solution to that equation? X is 0. Right? The only thing you can ever multiply times 4 to get 0 would be 0 itself. And then this one, when we solve that, set that to 0, do I need to go through the work, or is everyone comfortable with the idea that that's 3/5? It's 3/5? Okay. So we've got these. Let's just check real quick. Are we going to chunk them, or are we going to keep them? What's wrong? The 3 goes to the other side, right? When you set that equal to 0? We're going to keep these, right? We are going to check these because both 0 and 3/5 both live in here. So we're going to keep them. So we've got to check 2, right? And we also have to check the endpoints, don't we? I'm not quite sure why in my notes I said to check them in step 1. I don't know. All right, we're not done with step 1 though. What about this? Does this ever happen? Does our derivative never not exist? There's our derivative. It's good, right? There's nothing we have to worry about. You can plug 0 into this, that's fine, it just spit back 0. You don't get division by 0, you don't get any roots of negative numbers. It's a nice function, so no, this does not happen. We don't have to consider it. I am going to go to step 2, because step 2 I'm supposed to plug in the endpoints, right? I'm going to just plug everything in now. I need to do f of -1, I need to do f of 4, I need to do f of 0, and I need to do f of 3/5. Right? That's the 2 endpoints and the 2 critical numbers all being plugged into the function, and we're just going to compare all of these. So here, I'll do this one. There. That one's the easy one, right? Plug 0 in, you get 1. How about -1? So what happens when you plug -1 in here? You get a -1 still, then times 4. So -4. And then what about here? -1 here to the 4th power. It's +1, but then you still have -3, so -3, and then +1. So this is -6. So far, that's our minimum so far, right? And that would be our maximum so far, but we got to check everything. How about 4 when we plug 4 in here? Uh-oh, big number. 4 to the 5th power. That's big. You done it? 3329? Oh, did you hit it with the 4 or no? Is that 4 to the 5th? Or is that 4 to the 5th times 4? That's just 4 to the 5th?
No, 4 to the times 4. 4 to the times 4 to the power 5.
Okay, so that's this right here? Okay, and then what? Minus? I better get my calculator out so I can. Oh, that's the whole answer. Oh, that's the whole answer. Okay, so all right. Okay, good. So that looks like the max, the new max. And then 3/5. Well, 3/5, that's just going to really suck, isn't it? So this is where I think a calculator would be a good thing. All right. What do you get? 0.92. Roughly, approximately. Is that okay? I'm going to check these answers with the graph here in a second, all right? But this looks like our min, doesn't it? We don't have, oh, wait, no. Sorry, we have a negative number up here. This will be our min, won't it? And our max would be here. Right? Yes?
But it's not in range, is it? Or
What's not in the range? The inputs have to be in the range. It doesn't matter what comes out. Right? This is our domain. We're restricting our domain. We're only looking the x values. The x's have to be elements of that interval. All right, so I think the graph is going to be bad because it's got a huge scale. I'll see what Desmos says. So we're going to do 4x to the 5th, and then we're going to do minus 3x to the 4th plus 1. And then we're on the interval from -1 to 4. All right, so here's the graph. Well, look at this thing. It goes way up, okay, because it's at like 3,000. But look at the left side. Stops right there, right? And look at the y value. The y value is -6. But there's something interesting happening in here, and maybe we should look at that. We do have something interesting happening in the inside. Something is happening here at what value is that on the x-axis? Can you tell what it is? That's at 0, right? There's something interesting happening at 0. At 0, it's hard to tell, but it looks like we have like a little local max or something. And then this right here looks like we have a local min. And guess where that is? That's 3/5, right? At 3/5, and that's your 0.92. So the y value is 0.92, and the x value was the 3/5. So again, by doing this, we're actually picking up these points where interesting things are happening within our function. Now, of course, for this answer, our max is out here, way out there, way up there, okay? Questions?
Those two would just like what? Maximum min, it's not absolute max, right?
These are absolute maxes and mins. Yes, yes. As long as we're on a continuous function on a closed interval, it's absolute. All right. Let's try something else. X over x squared plus x minus 2. Okay. There's our function. Let's look at it first, okay? Let's actually take a look at the function first before we go about trying to graph it. And x over x squared plus x minus 2 plus x minus 2. Yeah, it's a rational function. I don't like this function. I want it to do something else. Yeah. Let's do this. Let's make the top squared. Yeah, there we go. And so we're going to change the problem. Yeah, there we go. That looks like fun. So let's make it x squared up here. Let's go minus x and plus 2. Sorry about that. But we'll get a more interesting result. And let's look between -2 and 4. All right, so what is the absolute max and min of this function on that interval, right? We have something that we have to worry about, and this is the first time that this has happened. We have to consider what the domain of the function is to begin with, because this is a rational function. We have to ask ourselves, is it possible that this could ever be 0? Because if this is 0, then we have division by 0, don't we? So what is the implied domain of this function? That's what we need to figure out before we begin. Because this is a continuous function. You can draw it without picking up your pencil, except anywhere where the bottom is 0. So let me just consider that for a second. Is this possible? Is it possible for this to be equal to 0? Like, where does that happen? Well, that's a quadratic equation, right? So let's just do a quick quadratic formula on this. Quadratic formula says that the solution to this are x equals negative b plus or minus square root of b squared minus 4ac. You all have that memorized, right? Got a tattoo of it on your arm or something. Right, so you've got that. So what is that for us? So negative b would be 1, right? That's b, that's a, that's b, that's c. So plus or minus square root. When I square b, I square that, I get 1 minus 4 times a, which is 1 times c, which is 2 all over 2 times 1, right? So that's me just plugging in. And right now I can stop. Why? It's undefined because this right here, that piece right there is going to be a negative number. And as soon as I know it's negative underneath the radical, that means there are no real solutions to this. And that means that this denominator will never be 0. Okay? If this problem was changed to a minus 2 right here, it would have worked. And you would have had to have considered that it has a restricted domain. All right? So in this problem right now, the domain of this is all real numbers. The graph of this should exist everywhere. All right? Now let's proceed. So I need to find the derivative. So the derivative of this function is 2x times, okay, minus 2x minus 1 times x squared all over x squared minus x plus 2 squared. And that's what we called the raw derivative, right? That was the raw derivative. All right? And I was pretty happy just to see you get that. But I told you at some point you would have to do some algebra on this, right? So try and clean things up if you can. But today is the day where we have to work with this now, all right? So I need to take that and set it equal to 0, don't I? So what I'm going to do to start off is I'm going to start cleaning it up. So I'm going to start distributing this through, and then over here I'm going to distribute that through, and then be very careful with that minus sign, right? So let's see what we get here. 2x cubed, that's here, minus 2x squared, and then plus 4x. And then here, when we do x squared times 2x, we get 2x cubed, but then it's subtracted. So minus 2x cubed, very happy to see that. And then when I do x squared times this, I get negative x squared, but then I change it to plus. So plus x squared. And then all of this over. Now on the bottom, do not square it, okay? We will try and avoid messing with that. And you'll see why in a second, all right? Let's continue cleaning up. Y'all see why I was happy to see the minus 2x cubed? Okay, so this is equal to, how many x squareds do we have? Negative 1. So we have negative 1x squared, and then plus 4x, and then all of that over x squared minus x plus 2, that entire quantity squared. I think that's a pretty cleaned up version of the derivative, yeah? So now we have to ask ourselves, when is this 0, right? Okay, so when is the derivative 0? Now, did we talk about this? I feel like I told you about this. If you ever see a fraction equal to 0, what's the only thing you have to worry about? You multiply both sides by b, right? So we did do this, right? A fraction can only be 0 if the top is 0. So that becomes this. So I have to take this fraction and I want to know where it's 0, right? When is that fraction 0? Only when the top is 0. That's why I said don't multiply out the bottom. Because really it's not worth it, because in the end you're going to not even look at it. So don't waste your time. Got it? So let's take a look at that now. The top of that is 0 where? So negative x squared plus 4x equals 0. That's all I'm looking at. So let's pop an x out, right? And we're going to get negative x plus 4. Like that. And then you set each of those factors equal to 0. So one answer is 0, and the other answer is, what's that? Positive 4. We have 2 critical numbers so far, right? 2 critical numbers. Do these live in our interval? Yep, 0's in here, right? Is 4 in here? It is, right? It's in there because of this. Oh, I have to ask you all an opinion on something. I'm going to do this off the record because it's really not related to the class, but it is. Okay, so both of these are included in our inner. I did. Thank you, though. Appreciate you telling me that. But I did. Okay. So both of those are in here, so we need to test both of them. Now, it just coincidentally, the endpoint is one of our critical numbers. It happens sometimes. So you don't have to test it twice, just test it one time. All right, so here comes the testing part. Oh, no, wait, hold on. No. Is our derivative not exist anywhere? And I just erased it. But my derivative had a denominator in it, didn't it? What was the denominator of that derivative? It was x squared. It was that whole thing, right? Squared, right? And then up here was the negative x squared plus 4x. We're asking ourselves, does this thing ever not exist? It might, right? It might if the denominator is ever 0, right? But we've already looked at that denominator. Haven't we already looked at this? I mean, it's squared now, but that's the same denominator that was here. So this is never 0, right? This had no solution. But do you see, at least now we have to consider it, right? So this right here, this cannot be 0. Therefore, this doesn't happen. We don't have any problems with an undefined derivative. Make sense? Sure? Okay, now step 2. So I'm going to take the endpoints, plug them in, and then I'm going to take my critical points, but I'm only going to be using 0, right? Because this one's already over there. So we plug these in. So negative 2 into this thing, we get 4 over 4 minus negative 2 plus 2. What do we have there? 4 plus 2 plus 2. 4/8, 1/2? 1/2. Then we plug 4 into that. So 16 over 16 minus 4 plus 2, which is 16 over 14. All right. 8/7. You just double check my arithmetic. You know my brain doesn't like arithmetic. So what happens when we plug in 0? 0 over 2, right? Which is 0. So there we go. I believe that's our minimum number, right? That's our minimum number, 0. And what about a max? 8/7. So on that interval, negative 2 to 4, the maximum value that we achieve is 8/7, and the minimum value is 0. And we can go back to the graph now.
Didn't we say it couldn't equal 0?
What couldn't equal 0? No, we said that the denominator could never be 0. There's no x I could ever pick that would make that whole denominator 0. Can you plug 0 in? Yes. 0 can go in, it's fine. All right, so there's the graph. Let's do the interval, negative 2 to 4. What did I do wrong? What did I do wrong this time?
Even set x negative 2. No, negative 2 greater.
I thought that's, oh, yeah. I always have different syntax in my head. This an x less than equal. There we go. That's cool. I like that. That's a cool little picture right there. So we looked at that graph just right there, right? In between negative 2 and 4, I can tell you that the smallest value you get is 0, and it actually happens at an x value of 0. So at x equals 0, we are 0. And then the maximum value occurs at 4, and that's 8/7. And then at negative 2, it happened to be 1/2, but that wasn't a max or a min. All right? Okay. So what we're going to do, what we're leading up to here, we're going to get all these techniques in place. How do we find the absolute max and mins of functions? We're going to move on to the next thing, which is what if we're not on a closed interval? Then after that's all done, we start doing word problems, where within the word problem, what we're going to try and do is take a real world situation, turn it into a function, and then try and find the highest and lowest points on that function. But we need to know how to do it first. I think y'all are ready for one. Let's do one. Well, I mean, I can sit here and wait, but I mean, it'd be nice to see one of these like right now, right? What's wrong? We can do a word problem right now. Okay, so look, this is a classic problem, all right? This is classic, like most Cal 1 students always, talk, oh yeah, I've seen this. Let's say that I want to build a pen for some animals that I have. I'm a farmer, whatever, okay? So let's say that I have, you have 400 feet of fencing material. Okay, you have 400 feet of fence. You wish to build an enclosure as shown. So let me draw the picture now, and then I'll ask the question. So we wish to build an enclosure as I'm about to illustrate. So let's say I'm going to make this as our first word problem. It's going to be very basic. I want to build a pen that when you look at it from the top, it looks like this. What I want to make are 5 identical pens. These are all identical dimensions. Okay? The question is, find the dimensions which give maximum area. So consider this. You have 200 feet of fence. I mean, sorry, 200. You have 400 feet of fence, don't you? I could do something really crazy like this, where I make my 5 pins really narrow. Oops, those are supposed to be, sorry, those are all supposed to look the same, okay? Maybe I make this like 4 feet right there, 4 feet, all right? And then that means this side's 4 feet, right? So how many 4-foot sections would I have? 1, 2, 3, 4, 5. I'd have 6 4-foot sections, right? So I used 24 feet of fence, right? So that leaves me how much fence left over? 376, right? Which I need to use for that side and this side. So what's 376 divided by 2? 188. So that means I make this 188 feet, and that will use all 400 feet. Does that make sense? 188 to build this side, 188 to build this side, that's 356. 4, 4, 4, 4, 4, 4. That uses all 400 feet of fence. And now I have my pins, right? What's the area of this total enclosure? What's the area? So multiply this 4 times 188, and what would you get? 752? Square feet, okay? I could do that if I wanted to, right? But I could build it a different way also. I could have done something like this. What if I make this 10 feet? Is the area going to be different at the end? That's a question you need to ask yourself. If I have 400 feet of fence, if I build it this way or build it this way, am I going to get the same area? So just reflect on that. Think about it. We're going to see right now, okay? So how much fence is used here? 60 feet, right? 60 feet, which leaves us how much left over? 340, okay. Divide that by 2. 170 feet here, right? That'll use all the fence. What's the area of this? 1,700 square feet. You get a whole hell of a lot more area building it this way, don't you? Do y'all see there's a difference? It's not just go throw it out there, we got 400 feet of fence, it's all going to come out to the same area. No. There is an optimal way to do this to get the most area out of your fence. Does it make sense? Yeah? You sure? So how do we figure that out? So does it seem difficult? I mean, like, if you don't know any calculus and you're just, out there trying to build your fence, then you're just going to kind of come up with something, aren't you? But there is an optimal solution. That's what we're going to do now, okay? Our whole goal right now is to try and find the maximum area, right? And the section we're talking about right now is finding the maximum and minimums of a function on a closed interval. So somehow this word problem is about to become a function on a closed interval. We have to make that happen, though. You ready to make it happen? All right. Okay, so here's how we're going to make this happen. Let's draw a picture again. Okay. What? I know, you told me. I know. She told me she was going to leave. I had to give her a hard time. All right, so I did an example just now where I made this 4, worked it out. We got an area. I made it 10, worked it out, right? So should we just keep trying a bunch of different ones? And no, we're just going to call this thing X because I don't know what it is, right? Right? Now, how many X's will I have? Well, I'll have 1, 2, 3, 4, 5, 6, right? So I have 6 X's. So what? I have 6 X's, big deal. What can you tell me about that? How is this 400 feet going to come into play here? Let me help with this. This right here, if we knew what that was, then we would know what the area is, right? So let's just call this Y. You okay with that? That's Y? And right now, do you agree